Hey everyone, welcome back to Power Electronics. I've been thinking about how these lectures are being delivered, and I decided that, I should probably split the lectures up a little bit. So we're going to be talking about switches in switch mode power supplies today. And we're going to this is like the first part, so we're going to divide it into a few sections, starting with switch utilization. So I'm going to introduce this concept, and then we'll look at other switches that we can use. So for the past little bit, we've been looking at kind of ideal switches in switch mode power supply. So this is a buck, right? And we've been imagining that Q1, when it's on, it's a short circuit, and when a switch is off, it's an open circuit, right? So that works perfectly well on paper, right? You can draw it out. It makes sense. However, eventually you're really going to need to build this, and you're going to need to use real things. So eventually we need to use real devices to implement these switches. And the question is, how do we choose devices? Maybe I'll make that question mark even nicer. How do we choose devices? Well, the way I'm going to discuss it is kind of how it's done in Fundamentals of Power Electronics, where we look at what the circuit needs the switches to do to operate, right? That's kind of one bit of it. And two, we're going to look at what the devices we have can do. And I'm going to be looking at diodes and MOSFETs, although there are other devices. These are kind of like the two primary ones. So in this lecture, we're really going to be looking at this, and a concept I want to introduce is the idea of switch stress. All right, these are kind of two important concepts. One is switch stress, like what the switch has to be exposed to when it's operating, and also switch utilization, which is kind of a measure of how effectively we use the switches in a device or in a converter. Cool. So let's get started. First, we're kind of interested in two separate things. The first thing in a switch, anyways, we're interested in two separate things. One is kind of the circuit level characteristics. So these are things like, well, primarily, how well does it approximate a short circuit when it's on? That's kind of one thing. And another thing is, how well or how does it approximate an open circuit when it's off. And like maybe you'd expect that devices can do both of these things perfectly, but we'll see that that is really not the case, and we have to kind of think about how to do these two things precisely in order to make things work properly. So this is like how do these devices, how well can they approximate an ideal switch? And then on the other side, we're kind of also interested in, device level characteristics. So these are things like how much conduction loss, like how much loss is associated with conduction when it's actually conducting current, no device is an ideal, nothing is an ideal short circuit, right? There's always some kind of, resistance or something. And there's loss associated with that resistance when it conducts current. So how much loss? Like how good can we make this device for, some given constraints? 2, how much voltage can we block? And how much current can we conduct? Right, like how strong are these switches in a sense, right? Can we expose the switch to 1,000 volts, 100 volts, 10 volts? Like what are the limits? Can we pass 1,000 amps through this device? Can we pass 1 amp through this device? Right, these are kind of like device level stuff, and specific switches are designed for specific power levels. 3, maybe, how fast can a switch between the off state and the on state, and also between on and off, right? And these might not be the same. The characteristics might be slightly different. So these are kind of like the 2 different things we're going to look at. And today, we're going to look more at the circuit level characteristics, right? How it kind of fits in with our circuit diagrams. And then in future lectures, we're going to be looking at, how like specific devices. We're going to look at diodes and MOSFETs and understand, the losses associated with them and how they operate. Cool. So I'm going to give you an example. We're going to analyze a boost converter. Okay? And we're going to look at what the switches are doing in a boost converter. So what is a boost converter? A boost converter looks like this. We have our input source, an inductor, a switch that goes to ground, a switch that goes to an output cap, right? So this is a simpler converter, right? There's one inductor, so one capacitor. We have our load resistance. Again, we're modeling our loads as resistors. This is our output voltage. We have Q1 and Q2. Cool. Very simple device. So this is what we're going to be analyzing. Let's get to it. So how do we do this? We split the converter up into its 2 switching states. The first state is when Q1 is on and Q2 is off. And here I'm going to explicitly draw the place where Q1 and Q2 are, even when they're off or on. Right? So this is where Q1 is. And then, so this occurs, right, between 0 and DTSW. And the second state is when Q1 is off and Q2 is on. And this is between DTSW and the end of the switching cycle. Perfect. Okay, so let's label some stuff, right? So we have our inductor, we have our inductor voltage, we have our inductor current. We have our capacitor, right? We have our capacitor voltage and we have our capacitor current. We have Q1, and we have the voltage across Q1 and the current through Q1. Right, I guess I should do this over here as well. Right, maybe this is where it's more relevant for this particular device. And we have Q2. We have the voltage across Q2 and the current through Q2. And again, everything is kind of over here as well, right? This is the same, it's the same circuit, just drawn at a different time interval. And there's also Q, but there's not enough space. But I hope you guys can understand what's going on. Perfect. So this is our circuit, right? And I'm going to analyze it in the way we've analyzed it before, but I'm going to include the voltages and currents across the switches. So we start with the inductor, VL. VL in the first state, VG, so this is VG over here. The input voltage, VG, minus, well, 0, right? This node is 0 volts. So VG across VL. In the second state, VG at the positive terminal minus, well, this is a short circuit, so this node is V out. So it's VG minus V out. And here I've already applied small ripple approximation. Great. Now, IC. IC in the first state. Wrong color, sorry. IC in the first state, we're going to use this orange color. IC in the first state, well, at this node, there's only IC flowing and the output current, so IC must be equal to negative at the output current, V out over R load. And in this state, IC is equal to, well, we have IL flowing through this circuit, through this wire, and I out flowing through here, right? So IC must be equal to IL minus V out over R load. Great. Okay. So IQ is equal to IL in this state, right? There's only one loop here. The current flowing through the switch must be the current flowing through the inductor. IQ1 is equal to IL. VQ is 0, right? So I won't even bother. We only really care about the current that the switch conducts when it's on and the voltage it blocks when it's off. So here the switch is on, right? So we care about the current, and Q2 is off, so we care about the voltage. VQ2 is equal to, well, this node is 0, and this node is minus V out, or is V out. So the voltage across the switch must be minus V out. And again, I've applied small ripple approximation here. Great. In the second state, VQ1, right? Q1 is off. The voltage across Q1 is, well, this is a short circuit, so this node is V out, so it blocks V out. And IQ2 is on, so we're worried about the current it's conducting. And it conducts, well, IL, right? Because this current IL has no place to flow other than through the switch. Great. So we can do IVSB really quickly here. So what does it say? It says that the voltage applied to an inductor. Let's draw this out so you can actually see what's going on. The voltage applied to an inductor over one switching cycle, averaged over one switching cycle, let's say, is equal to 0. And if I write this out very quickly, we have D times VG plus D prime times VG minus V out. This is the shorthand way, right? It's equal to 0. What this says, if you simplify it, is that V out is equal to VG over D prime, which means that M of D, the conversion ratio is 1 over D prime. Great. And we can do CCB as well. Again, I'm going through it quickly because we've gone through this before, and I assume that you understand how to do it. And if not, you can look back at other videos. Great. So the current applied to a capacitor over one switching cycle must be equal to 0. The average current applied to a capacitor over one switching cycle is 0. So if I do this quickly again, we get, well, minus V out over R load plus D prime IL, the average IL minus V out over R load. And that's equal to 0. Okay, cool. And if you simplify this, what this says is that the average inductor current, again, I didn't apply small ripple approximation per se, I'm just saying that the DC component of the inductor current is equal to, in this case, V out over D prime R load. Great, right? And again, we kind of see the conversion ratio here in the inductor current. So the input current is the load current times the conversion ratio, and the output voltage is the input voltage times the conversion ratio. That's kind of something that you'll notice. Cool, so we have the voltages and currents in terms of, well, we can do it in terms of the input voltage and load current, right? Great, we've solved the DC solution. So next I want to look at this idea of switch utilization. So we could draw actually, very quickly, we can draw the waveforms. Because why not? It's good practice, right? So we have one switching cycle with 2 subintervals. Right, the first thing we do is the inductor voltage, then the inductor current, then the cap current, then the cap voltage, right? This is pretty conventional. Wonderful, let's do it. So, VL, in the first subinterval, it's VG, in the second it's VG minus V out. The inductor current, the average is V out over D prime R load. And you can put this in terms of the input voltage, whatever. We're just doing it quick. So in the first subinterval, we're charging up the inductor, right? And in the second, we're discharging it. So it increases here with the slope of Vg over L, and it decreases here with the slope of Vg minus V out over L. Perfect, okay. The capacitor current, IC. In the first subinterval, it's equal to minus V out over R load. In the second, it's equal to IL minus V out over R load. Notice this is a time varying signal, right? So in the first subinterval, it is equal to minus V out over R load. And in the second subinterval, it's equal to the inductor current, right? This thing, minus V out over R load. So this average is, you can write the average V out over R load, D prime minus V out over R load. Cool. Then we can draw the capacitor voltage as a function of time. These are all a function of time, right? I hope you can agree with that. So in this first subinterval, we know what the average is, just V out, which is equal to Vg over D prime. So here, in the first subinterval, the output voltage is decreasing with the slope of V out over R load over C, right? So this slope is V out over R load C. And here, it's initially increasing with some slope, and then that slope decreases over time. So it's quadratic, right? Because this is a linear function, and when we integrate a linear function, we get some kind of quadratic. So we're approximating this as a quadratic with this concavity, right? Or convexity, whatever you want to say, right? So it's sloping like this. Great, so we've basically done the DC solution and looked at the waveforms. We could derive ripple equations, whatnot. But what I'm more interested in here is what the switches are exposed to. So let's recap. So for Q1, the voltage that this switch must block. Let's use, what color? I use this green. So we're interested in the maximum blocking voltage typically, right? So Q1, VQ1, the voltage that this switch must block is equal to, again, when it's off, it must block V out. And this is a positive voltage. And then the current that it must conduct, sometimes we like to think about the RMS current. The current that it must conduct is equal, so when it's on, it's conducting the inductor current. And if we want to consider the RMS of this part, right, so it's conducting, IQ1 is actually conducting this current, right? When it's on, it conducts this trapezoid current. Cool, so if we ignore the ripple, which we maybe shouldn't, but just for convenience, I will ignore the ripple here. The RMS of this waveform, turns out, this weird trapezoid waveform, the RMS of this over this switching period is equal to root D times the average. Again, with the ripple, there's some extra term. So I could be more precise. So if we included the ripple, the average to peak ripple, delta IL, then you'd actually get this extra term, which I believe is 1 over 3 squared times IL. But we just won't ignore, we won't pay attention to this bit for now. We'll just consider this root D times IL. So one thing to note, first of all, this current is always positive. And the RMS is equal to, we're saying, root D times IL. So we'll just say root D times IL. And this is positive current. So one thing we can do is kind of visualize this. We can visualize the necessities of this switch. And we can do it in this way. We draw an IV graph, right? So here we have V, here we have I. So this switch, what is required? It needs to, I'll use this blue, it needs to block positive voltage. So here, all it needs to do is block this voltage here. And it needs to conduct some always positive current, right? So the current is always positive. So in some sense, the requirements are a single quadrant, right? This kind of only occupies one quadrant. These two lines, the conducting line and the blocking line, kind of encapsulate this quadrant over here. So we say that we need a one quadrant switch. So it doesn't need to block a negative voltage, it doesn't need to conduct a negative current, it just needs to block positive voltage and conduct positive current. So in some sense it's a very restricted kind of switch. It doesn't need to be ideal. An ideal switch would be able to block positive and negative voltage when it's off and conduct both positive and negative currents. However, this thing doesn't need to do that. So because it has a more restricted, it has restricted requirements on what it needs to do, it's a bit easier to implement, right? So we just need to find a device, and we'll talk about devices later, that is able to do this, it's able to conduct positive current and block positive voltage. When we find that device, we can just stick it in. Cool. So that's Q1. Let's look at Q2, right? What does Q2 need to do? Let's use this green. Okay. So VQ2, the peak blocking voltage, right? We're interested in peak blocking voltages and RMS conducting current. So the blocking voltage, what voltage does it need to block? When it's off, it blocks the output voltage, right? Minus Vout, right? So a negative voltage. It needs to block a negative voltage, right? And really, you could argue that it is just depending on how I define these voltages right here. And that would be true, but then the current would be a different direction. In any case, what I'm saying here is that this is a negative voltage. Cut and dry, right? We need to block a negative voltage. And the current that it conducts, IQ2 RMS, is what? Well, in the interval when it's conducting, it conducts IL. So that means that Q2 actually conducts this portion of the current, right? So Q1 conducts the first portion and Q2 conducts the second portion. And by similarity, we can say that the IRMS for this part is equal to root D prime, right? Because it's kind of the same thing, just flipped around, and this is D prime TS. So the RMS that it needs to block is root D prime times IL, right? This is the RMS current of IQ2, and this is a positive current. And again, we can visualize this as well, right? In the same way, using this IV characteristic. So we have V over here, we have I over here. And I want you to notice that this is actually different, right? So it has to block a negative voltage. And it conducts a positive current, right? So the quadrant that it occupies is this one over here, right? So it's a different quadrant. So these two characteristics, these are different. Which means different switches are required, or devices are required. And we'll get into that a little bit later. Cool. So again, just to highlight, what we've done is by analyzing the blocking voltage and conducting current of Q1 and Q2, we're able to determine the requirements of the switch that we're going to use, right? For Q1, we need to conduct positive current and block positive voltage. For Q2, we need to conduct positive current and block negative voltage. Great. So that's kind of like the circuit level thing. And then this idea that I wanted to introduce of switch stress is still kind of circuit level. It allows us to compare different circuits. So let's get on to that. Switch stress. So this is simply, I mean, you can define it in a few different ways, but the way I'll define it is the product or the sum of the products of blocking voltage and RMS current of active switches. And by active, this means are, actively turned on and off. So a diode turns on and off naturally, but a MOSFET, you need to apply a voltage to turn it off. Turn it on or turn it off, right? So that's what it means by active. So S, the stress, is equal to, we're summing over active switches, and it is equal to the blocking voltage of that switch times the RMS current of that switch. Right? So this tells you, how hard the switch has to work. In a sense, cool. And then we can continue this, we can normalize this by thinking about utilization. Which is kind of like stress normalized to output power in a sense. So switch utilization, U, is equal to the output power divided by the stress. Right, so you find the stress, the blocking voltage and conducting current or RMS current of the active switches in a topology, and you find the output power of the topology, and by looking at the division of these two, you end up getting U as some function of D, and this kind of can tell you what conversion ratios the topology operates best at. Or not operates best at, but best utilizes the devices, the silicon devices in the circuit. Let's find so this is like active plus passive. Right? This is just an exercise to show you what it would look like. So let's find the total stress of the boost. So S is equal to, well, all we're going to do is going to take the product, right? The blocking voltage of Q1 is V out, and the RMS current of Q1 is root D times IL. So for Q1, we have V out root D times IL. So this is for Q1. And then for Q2, we have V out and root D prime times IL. And we're just taking the absolute value because if it blocks a negative voltage, that's still like some stress that it undergoes. The negative doesn't really like counteract anything. It's just the direction. Right, so this would be the stress, right? And you can see that it's related to the output voltage and the inductor current, so it's kind of hard to compare to other things. However, if we look at the utilization instead, which is really V out times I out over S, then we can find something that's a little bit more comparable, right? So again, this isn't the real utilization as defined in fundamentals of power electronics because we're looking at both switches and both of them may not be active. However, this is kind of just an exercise, right? If you were to use two active switches, then this would be the stress of this boost converter. So V out over I out, that's our output power. So what we should do is find everything in terms of V out and I out. Well, what do we know about IL? IL is equal to V out over D prime R load, or really, we can rewrite this, right, as I out over D prime, and that's what I'll do, right? So IL is I out over D prime. So recall, IL is I out over D prime. Great, so let's throw that in here. So we have V out times root D, and then we have I out over D prime, and then we have V out times root D prime, I out over D prime. Great. So now we can start canceling stuff, right? We can cancel the V outs, we can cancel the I outs, and then all we're left with, and this is kind of the power of looking at utilization, well, all we're left with is, well, we have D primes over here, D primes in both terms, so we have D prime, and then we have root D plus root D prime. So this is only a function of D. So like we could minimize this over D to find best utilization point. And maybe this is a good place to, that would be a good place to start your design. So this is really the only topic that I wanted to introduce. This is what I wanted to introduce today. So for me, this is a great place to stop. And next lecture, we're going to be talking about diodes. So we figured out how to characterize switches. And now we're going to look at specific switches we can use to implement our ideal switches and converters. Thanks.